In today's lesson, we're going to be looking at the double angle formula. So in a previous lesson here, I'll link that in the top right-hand corner, we had done compound angle formulas for both cosine and tan. And what I want to make note of here is that with these formulas here, if you let y equal x, you will generate what's called your double angle formulas. So starting us off here, we're going to look at these formulas we've been discussing, and we're going to let y equals x, and that'll generate some double angle formulas for us to reference. Let's take a look at our first. So taking a look at our first compound angle formula here, we have the cos of x plus y. As you know, it breaks up into the following equation here. Now, if we let y equal x, what will happen here, this will end up being cos squared x minus sine squared x. So now we have here one of our formulas here, the cos of 2x, and that can be written as cos squared x minus sine squared x. Given the fact that the sine squared x plus cos squared x is 1, we can now get rid of the cos squared of x, and I can substitute that with 1 minus sine squared x. Simplifying, we get a second version of the cos of 2x, and doing the exact same trick, this time getting rid of the sine squared x and writing that as 1 minus cos squared x, we end up generating 2 cos squared x minus 1. So therefore, the cos of 2x can be written in three different forms: cos squared x minus sine squared x, 1 minus sine squared x, or 2 cos squared x minus 1. Keep in mind, as we go through these formulas, we're going to have lots of different versions of these equations. You can generate all of them just remembering one of them. So for instance, if you can just keep your memory on cos of x plus y formula, quickly letting y equal x, you can generate this one. And then remembering your identity, sine squared x plus cos squared x equaling 1, you can go ahead and generate your other two. All right, let's take a look at the sine of 2x formula. For the sine of 2x formula here, notice this is the general form for the sine of x plus y. Letting y equal x here, this now becomes the sine of 2x, in which case we end up getting sine x cos x plus sine x cos x, and that becomes 2 sine x cos x. So now we have a version of the sine of 2x formula equaling 2 sine x cos x. Let's take a look at the tan of 2x. So in the next example here, we have the tan of x plus y formula. As you know, it's tan x plus tan y over 1 minus tan x times tan y. If you let y equal x here, we end up getting the tan of 2x, obviously. And on the right-hand side, we get tan x plus tan x over 1 minus tan x times tan x. And then we have generated our, after simplifying, our tan of 2x formula. So the tan of 2x can be written as 2 tan x over 1 minus tan squared x. Let's take a look at some examples applying our double angle formulas. For the first example here, we're given the tan of theta is negative 3 over 4, and we know that theta is between pi over 2 and pi, and we want to find the sine of 2 theta and the cos of 2 theta. To find the sine of 2 theta here, recall the sine of 2 theta, as we just found out, is equal to 2 sine theta cos theta. So therefore, if we can find what the sine of theta is equal to and the cos of theta is equal to, we can sub that in and find sine of 2 theta. Let's take a look at our unit circle here. Looking at our unit circle here, we're given the tan of theta is in our second quadrant here, and the tan of theta is defined to be opposite over adjacent, so we know that this leg of the triangle is 3, and this is 4, making this a 3, 4, 5 triangle, as you know. And again, if you don't understand where the 5 came from, you can just get that using Pythagorean theorem as well. So based on this here, we now know that the sine of theta in this quadrant will be equal to 3/5. And again, your sine is positive in this quadrant, so that's going to be 3/5. And your cos of theta is adjacent over hypotenuse. That's going to give us 4/5. However, in this quadrant here, we see that the cos is negative. So you have to tack on a minus sign on that 4/5. So therefore, substituting this into our equation, we end up getting 2 times 3/5 times negative 4/5, and we get the sine of 2 theta is negative 24 over 25. Notice here I can quickly find the cos of 2 theta as well. We have three different versions of the cos of 2 theta formula. I'm going to go ahead and use the cos squared theta minus sine squared theta version. So cos squared theta, in this case here, your cos of theta, as we discovered, was negative 4/5, so this becomes a negative 4/5 squared. And sine of theta is 3/5 quantity squared, and that's going to be 16 over 25 minus 9 over 25, which gives us an answer here of 7 over 25. So therefore, for this example here, the sine of 2 theta is negative 24 over 25, and cos of 2 theta is 7 over 25. Let's take a look at another example. All right, for our next example here, we want to find a formula for the sine of 3 theta and express that only as a function of sine theta. So to start us off here, what we're going to look at is you can break apart the sine of 3 theta, and I can express that as a sine of 2 theta plus theta. Now, if you recall here, if we look at our generalized sine of x plus y formula we get, and you notice here if I apply my generalized formula here to sine of 2 theta plus theta, we get. All right, taking a look here, we have the sine of 2 theta, which we can substitute in for 2 sine theta cos theta. And I also have a double angle formula here, the cos of 2 theta, and we have 3 different options for that. Substituting in, we get. And you'll notice here the sine of 2 theta is 2 sine theta cos theta. And you'll notice here for the cos of 2 theta, I chose the 1 minus 2 sine squared theta. The other two options were functions of cos theta as well. So this was the only option where it's a function of just sine theta. Continuing on and simplifying, we get. And you'll notice here now, I need this to be a function of the sine of theta only. This is the only sort of part of the equation where I don't have that. So I'm going to substitute that in for 1 minus sine squared theta, and we get. Substituting in cos squared theta with 1 minus sine squared theta, I can then distribute, collect like terms. We get our final version here, and we have here the sine of 3 theta is going to equal 3 sine theta minus 4 sine cubed theta. So therefore, we've expressed the sine of 3 theta as a formula being a function of only the sine of theta. Let's take a look at another example. In the next example here, we want to find the exact value of the tan of 112.5. Right away, let's take a look at what we know here. Well, if I double 112.5, I end up getting 225, and that's one of our special angles on our unit circle. You'll notice here that this has an acute angle of 45 degrees. And within that quadrant here, we know that the cos of theta is negative 1 over root 2, and the sine of theta is also negative 1 over root 2. So therefore, we know the tan of 225 degrees, which is sine over cos, is going to be 1. So if we look at our double angle formula here, it must be the fact that the tan of 225 degrees is going to equal 2 times the tan of 112.5 degrees all over 1 minus the tan squared of 112.5 degrees. So since we know the tan of 225 degrees is 1, we get the following equation. We can then multiply across by 1 minus tan squared of 112.5, giving us. Bringing everything to one side, we get. So bringing everything to one side here, we see that we have a quadratic. Looks a lot like the quadratic x squared plus 2x minus 1. Let's go ahead and do our quadratic equation. So using our quadratic equation here, we end up getting negative 2 plus or minus. This ends up being the square root of 8. And we can simplify root of 8 to becoming 2 root 2. And divide out the 2's, we get negative 1 plus or minus the square root of 2. So therefore, the tan of 112.5 is equal to negative 1 plus or minus the square root of 2. Now, since 112.5 is located in our second quadrant, we know that the tan function must be negative in this quadrant, and therefore the answer to this value, the exact value for the tan of 112.5, and therefore the exact value of the tan of 112.5 must be negative 1 minus the square root of 2. Notice had I included negative 1 plus the square root of 2, that answer would have yielded a positive decimal place, and in which case we could not have been in the quadrant that we are in. So the exact value of the tan of 112.5 is negative 1 minus the square root of 2. Let's take a look at another example. In the next example here, we're given the cos of 2 theta is 7 over 12, and 2 theta is bounded between 3 pi over 2 and 2 pi, and we want to find the sine, cos, and tan of each of these respectively. So first thing to notice here is let's divide across by 2 and get a bound on our angle theta. Doing so, we get. So we now know if I divide across by 2 here in this equation, we can see that theta is between 3 pi over 4 and pi. If I want to find the sine, cos, or tan of theta, just the angle itself, let's take a look at our double angle formula for cos. Looking at our double angle formula for cos, we know that the cos of 2 theta is equal to 1 minus 2 sine squared theta is one of our options. We know the cos of 2 theta was given to us in the question as being 7 over 12. Now what I can do here is I can isolate for the sine of theta. Doing so, we get. So you'll notice that the angle theta is within our second quadrant here, which means sine is positive. So therefore, the sine of theta here can only equal the square root of 5 over 24. We can now use this value to solve for the cos of theta. And you'll notice here the cos of 2 theta is cos squared theta minus sine squared theta. We just found out that the sine of theta is the root of 5 over 24, so squaring it, we get just 5 over 24. Isolating and getting a common denominator, we end up getting the cos squared of theta is 19 over 24. And again, taking our square root here, we're going to have plus or minus as an option when we take our square root, but in that quadrant, that second quadrant, cos is negative, so this will be the negative square root of 19 over 24. So therefore, we have the sine of theta and cos of theta found here. To find your tan of theta, just a matter of dividing these out. Dividing these out, the tan of theta is equal to. So dividing these out here, we end up getting the tan of theta is the negative square root of 5 over 19. And again, those root 24s cancel. So using our double angle formula, we can find the sine theta, cos theta, and tan theta. Let's take a look at another example. In our final example here, we just want to simplify the following expression. So first thing we want to do is, if you want to simplify an expression here, we want to expand everything out. Expanding out the left-hand side, we're going to end up getting here sine squared x plus first times second times 2 gives us sine x, 2 sine x cos x. And squaring the last term, we get cos squared x minus the sine of 2x. Now, if we take a look here, we can see that sine squared x and cos squared x, that'll sum to become a 1. And we're left here with plus 2 sine x cos x. But again, we know our double angle formula here tells us the sine of 2x is going to equal negative 2 sine x cos x. And again, that negative sign came from the original question here. And you can see here we get cancellation on 2 sine x cos x, leaving us with a simplified value of 1. So sine x plus cos x, quantity squared, minus sine 2x, simplifies to become 1. That concludes today's lesson on double angle formula. Thank you.